and his research primarily focuses on the practical challenges of designing multi-agent systems, with an emphasis on designing reinforcement learning algorithms and tools that make designing decentralized autonomous agents quick and easy. He received his PhD at UC Berkeley in controls engineering under Alexandre Bayen, and has spent time at Apple Special Projects Group, DeepMind, Facebook AI Research, and Tesla. Welcome.
All right, really excited to be here. Thanks to Cooperative AI for inviting me. A couple quick things before we get started. One, Carrie in the audience suggested that an exciting thing about a talk was to raise the amount of hot takes, so I've changed the title of this talk. Thank you, Carrie. And the second thing is I tend to call on people with ask questions, and if no one answers the question, I'm going to call on someone. So in the spirit of cooperation, please someone volunteer an answer. So the title of this talk is Human Data is the Cherry of Human AI Interaction, Not the Cake. And what I'm going to try to convince you of over the course of this talk is that there is a way to build complicated AI agents that know how to interact with humans, mostly in a data-free manner. And why is this exciting? This is exciting because there's so many places where we want to deploy agents that kind of either know how to interact robustly with humans. So in self-driving, we don't necessarily want cars to really interact with each other. But going from there, we also have maybe cooking agents, agents that reason about what the next step in your recipe is, maybe why you're only cooking 4 items at the time instead of 5, why you made a certain step. And going even more interactive to what I'm kind of really excited about is kind of large-scale mixed human AI systems where the AI assistants are both co-pilots, collaborators, really help you with decision making. And one thing that has really underlied a lot of the research that we've been doing for a while is kind of sort of coming from the MARL community, the multi-agent RL community, where there's this sort of foundational tool that has been extremely successful, which is self-play, which is kind of one of the few ways we know how to build human-level bots. It's the underlying tool behind building human-level StarCraft, human-level Dota, superhuman Go. And what we've really wanted to do for a very long time is figure out how to take these techniques that are so good at building human-level and sometimes superhuman-level bots and apply them to the design of agents that are able to not beat us at games, but interact with us, operate in our society, understand our beliefs and norms, and make us better. And the challenge there has been that there's quite a gap between the type of games that we know how to use self-play reinforcement learning for and these type of games, right? So if we think about a game of Go is a zero-sum game, right? There is a winner, there is a loser, and in fact, there is in some sense a clear best way to play that doesn't matter who your partner is, right? And this is quite distinct from something like a human LLM team where an LLM needs to be cognizant of so many things about me, right? It has to learn about what I know, what I don't know. It has to learn about my preferences. It has to learn about my beliefs and all sorts of things like that. And so there isn't, in the context of this, necessarily one single good strategy that I can play that's going to work well with all humans, right? I really need to interact. And so the fundamental claim that I'm going to try to convince you of and tell you about and kind of build some intuition for why this might be true, is that even though these systems really require, on some level, modeling humans very well and knowing a lot about them, there actually may be a way to build mixed human AI systems using almost no human data. And in fact, in the case of this talk, we're going to use no human data at all. And the reason that I have this caveat here about almost is that I still think that there's a lot of really great uses that you can get out of human data. You don't strictly need it, but if you have it, there's a lot of good stuff you can do with it. And part of the reason I'm pushing back on this idea of using human data is that sort of with the exception of a few domains, the kind of standard thing that we get out of human data or models, they have these kind of common properties. First of all, human data tends to be extremely expensive to collect. Getting an RLHF sample is something on the order of $50 from a good human expert. When you collect human data, it tends to mostly be nominal. So it's not like when people collect data for self-driving cars, it's mostly driving in a straight line, right? Whereas what you really care about is like safety critical cases or really complex switch interactions. You just don't get them. They're so hard to collect. And then in many domains, human data or models that you might want to use to train your RL agent against are often unavailable. They tend to have extremely poor scaling laws. So like, if you want to build a great model of a human and then kind of train against it, you're going to actually wind up needing to collect millions or billions of samples. And so because of all these reasons, if human data or having really rich models of humans are the base ingredient on which we build our protocols for building human-AI interaction, then progress is going to be much slower than we would like it to be. And so over the couple of years, we have been trying to make a case that you can kind of get away mostly from human data and models. And so what I'm going to be talking about is our work mostly on building a human-compatible AI driver entirely from self-play. So if you're not from the self-driving community, a self-driving stack looks something like this. You have a perception system that uses LiDAR, camera, radar to look out in the world and figure out where everyone is, right? Often it's converting it into bounding boxes that describe where everyone is. That perception system is fit into a prediction agent, or kind of a model of human behavior, that says where everyone in the scene is going to go in the future. That set of trajectories about where everyone is going to go is converted into a set of plausible trajectories for your autonomous vehicle. And then, like, the planning phase is to go from those trajectories, cost them, figure out which one looks good, and then control will take in the selected trajectory and convert it into steer and action commands. And what we're going to be talking about, the reason I want to walk you through the stack is we're mostly going to be talking about this latter half, right? So we're going to be talking about building cars that already have great perception, but don't necessarily have prediction, planning, and control. And what we'll be presenting is an RL agent that generalizes zero-shot to held out humans using no human data at all. And I'm going to put air quotes on humans because this is going to be done entirely in simulation, so we don't have an exact model. But to the best extent that we can measure compatibility with humans in simulation, it looks like it's compatible with humans. And I want to spend a tiny bit more time than I normally would on the author slide of the paper that this comes from. So this comes from a paper called Robust Autonomy Emerges from Self-Play. And the reason I need to spend extra time here is that this is an equally joint project between 8 people. So Marco, David, Alex, Brody, Alexei, myself, and Eric all contributed equally to this with a late assist from Taylor, Killian, and leadership from Stuart Bowers, Ozan Center, Philip Graham-Buell, and Vladlen Colton. And so, yeah, it's not often that you get to participate in a project where everyone contributed to it totally equally. And so even though I'm the person who gets to talk about it, I want to make sure that all these folks get appropriate credit. OK, so the setting that we're going to be operating in is often called the ad hoc teamwork setting. Our goal in this setting is we want to create an autonomous agent that is able to efficiently and robustly collaborate with previously unknown teammates on tasks to which they are all individually capable of contributing as team members. So everyone on the team is useless. No one is actively, unhelpful. And the hard thing about this ad hoc teamwork setting and the hard thing about moving away from the zero-sum settings is that this caveat about previously unknown teammates is extremely hard to satisfy. It is extremely hard to build an agent that can efficiently and robustly collaborate with all previously unknown teammates. Why is this hard? An example that I quite like, that I think to me illustrates very clearly why it's hard to do zero-shot, is this Kiki and Booba example, which I'm sure many of you have seen before, but just really quickly, raise your hand if you think that the one on the left is called Kiki. OK. Raise your hand if you think it's called Booba. There is a single person who thinks it's called Booba, and you heard the challenge. Most people think the one on the left is Kiki because Kiki is a hard word, and this is kind of sharp. Most people think the one on the right is called Booba. And if interaction with me, before we interact at all, we have to come to an agreement that the thing on the left is called Kiki, well, an AI agent has no idea that that's called Kiki. I mean, actually, LLMs do know that this is called Kiki, so this example is getting a little iffy now. But you know, the fundamental idea is that if you need to model something almost exactly and kind of know a lot about humans, it can be hard to interact. And this example is cute, but I mean, more fundamentally, there are many things about your teammate that you need to know to interact with them very well, right? There may be conventions that you need to know about, you know, maybe you drive on the right-hand side of the road instead of the left-hand side of the road. There may be reaction time, right? I can't expect a human to react in under like 1.5 seconds most of the time. The teammates may have variable skill levels. So, you know, I need a policy that works well with beginners and works well with experts. My partners may have different levels of computational capabilities, right? They might be able to simulate short searches. They might be able to simulate deep searches, and I don't really know which one. And they may also have beliefs about the world that I may need to interpret to collaborate with them. And then on top of that, they may also have norms that govern what type of behaviors are sanctioned. And even though there are all these things that are kind of getting in the way of ad hoc teaming with arbitrary partners, I think that there is a perspective you can adopt that lets you get away from this. And I'm not sure if anyone has ever thought of the idea of representing things as a cake before, but this is what I call the cooperation cake. So the idea is that underlying cooperation are some set of basic capabilities, right? Everyone kind of needs to know how to drive their car. They don't just like suddenly steer off the side of the road for no good reason. And we can get these basic capabilities generally by scaling up RL. So we can build skills by really scaling up reinforcement learning. The other, and I think this is the foundational thing that I want to get across in this talk, is that there is a robust default. In most situations, there is a basic behavior that is not perfectly tuned for every teammate, but works pretty well for most teammates, for the classes of games that humans tend to play. And the way that we can build this into our systems is with a small amount of partner uncertainty. If we have a small amount of uncertainty about who we're playing with, their beliefs, their capabilities, and so on, and we don't even necessarily have to specify this correctly, this builds into the agent, this kind of constrains the set of possible ways we could cooperate, and leads to like a robust behavior that works with many agents. And then only at the end are these conventions, preferences, beliefs, norms necessary to specify exactly correctly. We can use this robust default for most situations, and when we want to really do well, we can use some amount of human data or adaptation to get that piece right. So I'm going to be talking to start about scaled RL and partner uncertainty, and kind of try to build your intuitions about why this might work. So the scaled RL tool that we're going to be using is called self-play. And the idea of self-play, which I suspect many people are familiar with, but just in case, is that we're going to have some policy or some agent, pi sub t, and it's going to play many games against itself. We're going to collect many trajectories of it playing with another copy of itself, pi sub t. We're going to take all of those games, we're going to put them into some black box training algorithm, and that black box training algorithm is going to spit us back pi sub t plus 1, a policy that is in some sense better than pi sub t. Internally, what every agent is doing in the self-play loop is they're just running your standard RL loop, right? They're taking actions, it's being fed into a simulator, it's giving you your next state and a reward, and then continuing to generate trajectories that way. And just to be clear, when I say that every agent is pi t, if we're thinking about a driving scene, then every agent is driving around with a copy of pi sub t on itself, right? Everything is totally decentralized, but every agent has an almost identical policy running around. And so a question I want to pose to you all is imagine that I have this setup, right? I have a bunch of driving agents at an intersection, right? And I'm running self-play RL. And every agent knows the goals of every other agent. It knows the capabilities of every other agent. It knows that we're in a mostly noiseless world. And it really knows exactly the policy of its partner, and it knows exactly where it's going to go. What would this likely look like if I simulate this forward and I learn the optimal policy?
We'll just cross each other perfectly, like in a march, kind of Chinese military march.
Yeah.
Type thing, but it'll be super brittle to other unknown.
Yeah, exactly. So they're going to be extremely over-coordinated, right? But in a way that doesn't generalize to any partner outside of that self-play thing, and that is exactly what happens, right? And I think generally you don't want your self-driving car to do this. I mean, eventually probably you do, but not in the short term, not when humans are in the loop. And if you really put humans in this scenario and you like kind of really break down the road rules, it looks a lot more like, you know, like, like this. And so what I want to get across is that even though that super over-coordinated equilibrium exists, it kind of goes away when there's a little bit of uncertainty. And so one thing I want to think about, or you to think about, is suppose that I have this heavy object, right? And I pick it up, and I want to hand it to you, right? I want to pass it on to you. How generally would you like hand this off to someone? Does anyone kind of have an intuition for how you would hand off a heavy object to another person? Yeah, you'd like hand it off both-handed. But then there's something else on top of that, which is that what you tend to do is that when you hand it off to them, you wait a little bit to see that they've kind of, the weight distribution has changed, right? And this is what humans do when they're handing off cups to one another. Like they hand it over, they pause, they wait for the weight distribution to change, and then they release. What they do not do is they do not throw it to their partner when they're interacting with them for the first time. But among construction workers, you do see that when they work together for a long time, they will throw objects to each other. And in fact, they will sometimes throw them like perfectly so that they're like the person can catch them exactly at its apex. So the idea is that under this partner uncertainty, when we have agents that have basic capabilities, that uncertainty is going to constrain the set of reasonable policies. There's not all that many ways you can coordinate at the minute you're a little uncertain about who your partner is. And so the way that we implement this in self-driving is we set up this large-scale goal-reaching game. We built this simulator entirely in PyTorch. Every GPU in that simulator can hold 4,800 copies of one of these maps. These maps vary a lot in scale, from 300 meters to about a couple kilometers in any direction. And on each of these maps, we throw up to 150 agents, and we throw goals all over the map. And we just tell agents, drive to your goal under uncertainty about what your partner's goal is, and with some uncertainty about the rewards and capabilities of their partners. Locally, each agent sees kind of a view around itself. So this is kind of the perspective from this dark blue agent. It sees the cars around it. It sees the edges of the road. It knows where its goal is. And that's kind of all it knows. And all of this gets fed into a really small little neural network. And the way that we generate uncertainty, atop the fact that we don't know where our partner's goals are, is we use this nice technique that we call like reward conditioning. It's not a new idea. What's kind of new and cool about it is that it works really well. So what we do is there are some n reward terms in the system, and every reward term has a weight. And we sample those weights from a distribution, and we provide the value of those weights as an input to an agent. So every agent has a different reward function. It knows which reward function it has, but it doesn't know the reward function of the other agents in the system. And so this can look like things like being very incentivized to drive in your lane. And if we vary the weight on this being incentivized to drive in your lane, we can go from really caring about driving in your lane to forcing the agent to actually drive in the opposite lane, like on the wrong direction of the road. Things like caring about getting to your goal very quickly or not. Things like caring how much like your heading is aligned with the lane. Things like caring about how jerkily you drive, and things like that. And then each of these weight terms is sampled from a distribution and provided as an input to our neural network. What does this all look like when we put it together? It looks kind of like this. So this is one of the worlds that we're simulating forwards. Kind of watch this area over here, because some of these agents are quite weird and love to do U-turns in the middle of the highway. So I'm going to give it a second to make some choices about where it wants to go next. And so you're driving in this really like rich, complicated world where kind of anything can happen next. There's a huge amount of uncertainty about your partners. If one car crashes into another car, it stops in the middle of the road and becomes a blockade. And then we have these cars drive around in this world for the equivalent of 10,000 years of human driving. To kind of like put that to scale, over here we have the total amount of open source human driving data. It kind of corresponds to about 0.05 million kilometers. And if this is the sun and this is Saturn, this is about how far we drive. So 1.6 billion kilometers. And kind of thinking about that cake and the lessons we've learned from kind of training LLMs, this kind of scale is really fundamental to the results we see. There are things that we're going to see that don't happen below this scale. So thinking back to this example about kind of human-like driving, when we take our agents and we place them behind this obstacle, they don't want to drive through this obstacle. They do this like human-like nudging and priority that I've never seen agents kind of do before. And this doesn't show up below 1.6 billion kilometers. At 800 million kilometers, they're still like bumping into each other all the time. But then, you know, you get this. I'm obsessed with this video. Sometimes my students will just find me sitting there just watching it. As I've never seen agents do anything like this before.
Can I ask something?
Yes, please.
Don't they learn to remove the block?
They can't. They can't remove the block.
So there's no action space like that.
No, you could imagine that block is like a crashed car on the road.
Oh, it's actually an example of social graph where the best solution is actually to remove them so that they can all go.
Yeah, I mean, it would be possible to remove this, but I mean, let's just imagine that there's a road closure there for some reason. You know, it's not removable. And the point I want to make is you do not see this below a certain scale. So the y-axis here is the crash rate per million kilometers. And so over here, our cars are crashing once every million kilometers, which is humans crash between every 20 and 100,000 kilometers. And if you stop the training over here at about 50 hours, you wouldn't see this. And out here, all of a sudden, you do. And I'm not saying that you need 1 trillion samples of training to make this happen. There are going to be better algorithms that push this number down. But like if you don't really scale up, you don't see these kind of rich, robust behaviors. Yes, question in the back.
Do you have an intuition about why this is not monotone? Like you see this peak at 20.
Yeah, so the question is, why is this not monotone? The reason is because we're not, our objective is not maximizing the self-play crash rate. It's kind of getting to your goal. So it's kind of a misaligned proxy objective. It's a great question. Similarly, on benchmarks that people use to measure driving capability, we don't hit state-of-the-art on them until certain scales. So there's common benchmarks called Newplan. We hit it at 400 million kilometers, state-of-the-art. Carla, something around there. Waymax, a couple 100 million kilometers more. And then we only plateau in how we do on those kind of even further out in training. So to give you an example of like what doing well on one of these benchmarks looks like, this is what we're going to do here. The Newplan benchmark is kind of replays with human data. So you collect trajectories from Boston, Vegas, and Singapore, and you're going to replay them. So every orange car here is just following a trajectory observed before with a little bit of reactivity built on top, and we're going to be the green car. Sorry, bigger. Sorry, similarly, I also spend a lot of time watching these videos. Maybe skipping, yeah. Like this car is kind of ready for its model of the humans to be wrong. I don't know if you also saw that. One of the problems with these benchmarks is the trajectories can drive over each other. Where's the one I really like? Yeah, I really like this one. Just like kind of nudging around some pedestrians. It's a very stressful benchmarks. OK. So, and I also want to say one thing that I think is interesting in the world where we're kind of thinking about how to interface with RL and LLMs. The underlying policy that does this, that gives you this level of robustness, is only 3 million parameters. Like it's a tiny, tiny neural network. Which I think that means that sometimes like the actual planning problem, once you have the right representation, is quite compact. So if you're thinking about like how big do RL policies need to be to solve planning problems, they don't necessarily need to be very big. You just like most of the weights are going towards getting the right set of features atop which you can have a compact policy. Another cool thing, and I'll have a kind of prompted question about this at the end, is that these policies can be rapidly fine-tuned. So this is from a different paper that some of my students did. It's a little more restricted in some ways, but we kind of trained some agents to do something similar and drive to their goals. But in this paper, none of the goals are ever behind the agents, right? They never have to do a U-turn to get to their goals. And what we find is that having trained these basic policies, When we then place goals behind the agents, we can fine-tune to learn to do these U-turns and this interactive behavior in just like 10 minutes. So once you have this basic policy, it can be fine-tuned to do new tasks really fast, even if they're out of distribution. To draw like a couple more points, now that we have these kind of basic policies, we want to think about this last piece of like how do we build human data on top of them. And so if we go back to this Kiki and Bob example, an open problem to us that we're kind of really excited about and I think is unresolved is you have this basic model, you have some human data, how do I just extract that last layer from it, right? The human data both tells you what are the conventions and it tells you how to drive. And we don't care about the how to drive bit. We know how to drive. We just want the conventions out of it. So how can we use human data to just do that last piece, right? Or alternately, another problem that we've been thinking about lately that builds on top of this work is moving beyond zero shot, right? So I've specified, I have whatever model I built there before kind of knows how to drive robustly with the distribution of partners. But as I move away from this zero shot setting and I give it the potential to kind of drive and adapt to the agents around it, maybe it can learn those like that last layer, those like conventions, norms, beliefs on top through series of interactions. So we've been trying to work on this like kind of long horizon RL setting where you get multiple episodes of play with your partner and you can use those earlier episodes to kind of infer those last components. The hard thing about problems like these is this is like really long horizon reinforcement learning and it creates kind of technical engineering challenges. There's a question, yes?
About the previous open problem. So when you train in self-play, you will adopt your own kind of conventions naturally. Maybe through robustness, you will remove some of them. But
yeah.
There will still be conventions showing up.
Yep.
Do you regularize in some way to be able to adapt to all kinds of conventions? Or if not, then if you use human data to learn what kind of conventions are used in humans, you might have to change the policy completely, like a lot.
Yeah. So the question is like, during self-play, we're going to have some set of conventions. Those set of conventions are not necessarily easily transferred to a new, like we can't just necessarily switch from one set of conventions to another set of conventions with a small amount of fine-tuning on human data. I think that's right. And part of that's kind of a concern about this. And I think that one of the appealing things about doing this kind of K-shot setting is that what you might learn in the K-shot setting is inferring conventions and how to adapt to them. So instead of a policy that has a fixed set of conventions, you have a policy that has a starting set of conventions and then kind of quickly does active exploration to figure out what the remaining set of conventions are. Because it's true, right? There probably are some conventions that are so far removed from the basic policy that they can't be learned. So this is kind of a bit of a hypothesis, right? I suspect that there is some way to like quickly fine-tune layer on some conventions on top, or just even like describe the conventions in natural language or something. But I don't 100% know how to do it. That's why I think it's a neat open problem. It's a great question. So to wrap up a little bit, what we have, I think, built here in the system that we call GigaFlow, is sort of a pipeline for ad hoc teaming. There are kind of three major components to this pipeline. First, we have our goal-reaching game, right? We have some kind of highly interactive task. We're throwing goals all over the place. There's like some game we can scale up and generate, millions of trillions of interactions of, and use it to like train the base capable agents. Then we have some mechanism for specifying diversity or uncertainty. And in our case, it's this reward randomization, right? Every agent has slightly different objectives. And then we have some way of scaling this all up, and that's for us, that's self-play proximal policy optimization, which we find to be a useful algorithm here. It's not necessarily the only algorithm you can use, but it works here. And if we abstract this out and think about how we go beyond self-driving to problems that are perhaps more relevant or interesting to the cooperative AI community, what this looks like is some highly interactive task that we can use to generate these kind of base capable agents, some representation of uncertainty, and because I only know one hammer, scaled reinforcement learning to bring this all together. And we can think of a lot of things as falling into this box that are perhaps more relevant to this community than self-driving is. You could think about human LLM collaboration, right? So we could have some goal, for example, collaborative information discovery, right? Help me, let's find something on Wikipedia together. I have a lot of, I'm not the same as an LLM. I kind of have some understanding of the knowledge graph, and it has some understanding of the knowledge graph, and we can collaborate together to find it more efficiently than either alone. As our source of uncertainty, because we don't want to actually use humans here, we might use weak and strong LLMs, right? So that when they partner together, each LLM is uncertain about exactly how capable its partner is. It might need to ask it some questions to elucidate those capabilities. It might need to infer those capabilities when its partner brings back some information and it's not what it asked for at all. And then it could kind of put this all together. We could use scaled reinforcement learning. We could also think about collaborative construction as falling into this task, or any really collaborative human-robot task, right? So we could imagine task handoff as the thing we need to do. So for example, like just literally passing objects to each other. The uncertainty here being, again, some kind of randomized reward preference about how capably I want to do this task, my preferences about how the task is done, and so on. And again, scaled RL. Yeah, so putting that all together, I want to end with some quick acknowledgments. This is some of our lab members. We're always hiring, so come join us and work on building human-AI teams. And end with a sort of kind of summary points before we go to questions. In some domains, there may be robust strategies that work pretty well with almost all partners. Not every domain. We don't know exactly how to characterize the set of domains for which this is true and not true, where you can ignore, you can like partner with someone even if you don't have their convention right. But there's at least one, and I suspect that there may be many, many more. It is possible that these robust strategies can be quickly tunable with a bit of human data. We have some preliminary evidence that this is the case, but we have not made the case fully. And does this idea of training under a bit of partner uncertainty with some kind of highly interactive goal-reaching game? I think goal-reaching games can be quite general, in fact, if you generalize the notion of what a goal is, to build foundation models of coordination that can be reused. So with that, I'm at the end of my talk. If anyone has any questions, I'm happy to answer them. And after that, I have a couple of prompts that are just kind of for open-ended discussion.
Yes, question. This is kind of a technical one, I hope that's okay. You mentioned about the randomized reward conditioning. Yeah. So I've come across something which may be the same thing, but I don't think it's called that. And I was wondering if you talk about it just works, but is it the thing where it's like you have some space of reward functions and then you're sampling weights from that for an agent, pass the weights to the observation? It looks too good to be true, but it works.
It does work. Yeah, it works. It works. Huh?
Just a quick reminder.
Oh yes. So, and repeat the question. The question is like, we have a set of reward functions. Thank you. We have a set of reward functions. We sample one of those reward functions in that distribution. We pass it as an input to an agent, and then the agent kind of behaves somewhat optimally under that reward function. I mean, for this set of rewards, it really does work. There are other works in this space kind of studying similar ideas. There are things called like reward encoders. People do like zero-shot RL with like successor features and forward-backwards functions. So there's a lot of different works that actually try this thing. This, I think, in our case, having watched thousands of hours of videos of these cars, like it's quite robust. They really do obey the reward functions. I wish I had a nice video of it for you. But yeah, I think it kind of makes sense to me that like at scale, throwing a ton of compute at it over a finite set of reward functions, you can kind of learn the correct policy for it with a sufficiently expressive neural net. Yeah, I think it's like in some sense kind of obvious that it would work, and it's just interesting that it does because you never know. Maybe it wouldn't have worked for reasons unknown. Yeah.
There are some very upvoted questions on Slido, if I get to throw
let's
those
do
in.
that.
So one here was, how do you deal with settings that involve more adversarial agents, as well as more cooperative agents? Do you just use the same approach, or what changes?
Yeah, that's a great question. We mostly haven't thought about adversarial settings too much because we kind of are interested in this like kind of semi-collaborative setting. I think that we are actually extremely interested in working on this adversarial setting because in the adversarial setting, I think what you would see emerge here is the formation of like kind of stable coalitions or things like that, things that can work together to reject the adversary. So we're starting to try to apply these ideas to games like welfare diplomacy, where there is a cooperative task, there's the potential of adversarialness or defectors. So I think that one of the ways that you would apply this approach here is you would just mix in some set of adversarial agents who are unknown and have to be inferred through interaction. And then I think you would see the formation of like stable coalitions or coalition formation. You don't see this in driving because no human is really all that adversarial in driving. But I think there are some really interesting domains where you could ask this question, and we're starting to actually work on this in collaboration with cooperative AI.
Another one that got a lot of upvotes here is, how does your partner uncertainty compare to other ad hoc teamwork algorithms in this setting, like a maximum entropy population-based training, for example?
Yeah, I think there's actually a huge number of really great works on ad hoc teaming and ways of generating diverse populations that could create that source of uncertainty. A really nice thing about the reward conditioning, and actually part of what this all makes it all work, is that it all fits into one neural network. There's like a single policy that we use, and so that means when we're kind of scaling up training, we can do inference on all the neural networks at once, like on all the policies at once. We just stack them and like do a single forwards pass and get a million actions. So that's really convenient as opposed to methods that kind of maintain a population of agents that are distinct. Now these ideas can be fused together, and of course you could take any kind of diverse population-based method and try to put them all into one neural network by doing this type of conditioning in some way on some kind of latent. And I think that there probably are methods from the ad hoc teaming community that would also have worked here, right? We're one group of people. We only really got to try out one algorithm. This took us almost 2 years to do. So I think it would be extremely interesting to explore the relationship with other ad hoc teaming approaches, whether they work perhaps better. Yeah.
Oh, now it's changing the rating here. So another one popped up as the highest. What are the properties you think are needed for specifying games so that you can run uncertainty plus scaled RL in order to solve them?
Right.
Specifying step one. I'm not sure if the...
Yeah, so the question is like what properties are needed such that this kind of approach can work? Fascinatingly, this is also one of the prompts that I was going to give you, so you could tell me the answer. So I'm not going to answer that question because I want you to discuss and help me answer that question, if that's all right.
Yeah. Another one here was, how do you propose to model human behavior?
Yeah. So what we're doing here is we're actually treating these agents as a model of human behavior. Right? We're assuming that human behavior is mostly rational, and with like some preferences, conventions layered on top, and using. So actually, if you take the agents that come out of this, like these guys, and you go and you, I just want to leave this video hanging out. And you go and you like measure the closeness of these policies to human likeness, and there are benchmarks for measuring human likeness. They're not at the top of the leaderboard, mostly because they like to drive a little bit slower than humans do. But one way of modeling that is then taking these agents and using some of the free parameters to fit to data. And I think you can do that in lots of settings.
Cool. Here, I guess you touched on this a bit, but like, what does self-driving teach us about cooperation? Like, how can we apply the ideas of cooperation to self-play and self-driving?
Yeah, I think that how can we apply the ideas of cooperation and self-driving? I think that this is like an example that I think about a lot. I think many like human systems are quite a bit like this, right? When they're not governed by explicit rules, but more by like informal norms that have evolved out of an understanding of our capabilities. And so, like, I think that this idea of, creating this population and these base agents are kind of will somewhat be applicable to any setting where we have large groups of humans choosing to interact without a lot of rules. What kind of settings are those? I mean, I think, like, I think, for example, like, when I am pair programming with another human, or we are collectively building a code base together, like, there are not really a strict set of rules that we're all obeying, right? We're kind of doing this sort of thing of making choices that are robust to not having an exact model of what other people are doing. In fact, a lot of software development principles are kind of around the idea that, like, somebody else is going to use your code, they're not you. They're not going to understand exactly how you meant to do things, build things in a way that they're robust to partner misspecification. So I think that there are lots of systems that this can be used to simulate, and then having done that, to think about what it would be like when an AI agent is placed into that system. These are also kind of the only set of extremely capable reactive agents that I'm aware of that are also somewhat open source. Like, our lab has open sourced some versions of these, and they can be used to study human-AI interaction directly, right? Like how does a human behave if we place it into a pool of autonomous vehicles? And I think that kind of going to those other settings, they can also be used to create human proxies for the actual settings that you in particular care about, right? I'm not assuming that everyone in the room cares about self-driving, but I think that lots of systems look like this. Yeah.
Cool. We have a lot of questions, but if you wanted to save some time for also people discussing, like, it's your call when we...
let's do one more question and then go to...
Yeah. So one question here was, why is the long horizon not a problem in self-play?
Why is the long horizon not a problem in self-play? The long horizon is a problem in self-play. It's a huge problem. It's part of why we need this level of scale, is it's very hard to optimize extremely long horizon problems. I don't have a graph here, but you can see that the value function that this policy learns thinks like several hundred steps forward. Like, sometimes there will be an obstacle like hundreds of meters away, and the car will preemptively reroute itself to go around that obstacle. So it's learning very long horizon reasoning, and it takes a huge amount of time for that long horizon reasoning to propagate through the value functions, like when you're doing like TD learning and things like that. So I think that's part of why we need this huge scale. There are going to be better, more efficient architectures, more efficient algorithms that handle it, but long horizon is just a fundamental problem. Yeah. Okay, so I thought, you've listened to a bunch of talks. There was a talk before mine that was fantastic, and I actually bought the textbooks that were listed. But so I thought it might be fun to just like talk through some prompts. I have some prompts that I think are kind of related to the ideas here, and I'm curious for your thoughts on them. The first question, and you can maybe discuss amongst your groups, amongst yourselves, is, I have some set of ideas about how you're going to design mixed human AI systems, right? I'm sure you all bring your own set of techniques and tools to it. Would you design mixed human AI systems this way? What type of mixed human AI systems are interesting? And how would you design them instead? So I think you're collectively at tables, and you can, discuss amongst yourselves, and I'd love to hear any thoughts that folks have.